Let's talk about a few examples. This first example involves a first-order linear differential equation. If we're going to apply our general existence and uniqueness theorem, we have to put it in the correct standard form. This is one possible standard form for a first-order linear differential equation, but not the one that applies in the theorem that we had. In order to use the theorem, we need to write this as y prime plus 1 over t y equals 1 over t times 1 minus t, t minus 1. Though it wouldn't make any difference. Quantity squared. And this is our function g of t. This is our function p of t. And this is our function g of t. And then we have to ask, on what intervals are both p and g continuous? And it's pretty easy to see for these functions p and g that the only places they're bad only at 0 and 1. In other words, on the interval from minus infinity to 0, we're okay. On the open interval from 0 to 1, we're okay. Or on the interval from 1 to infinity, we're okay. What does that mean? That means if you give me an initial condition to go along with this differential equation, and that initial condition is the specification of a value of y at some point t in this interval, you'll be guaranteed a unique solution to the initial value problem that's valid on this entire interval. Similarly, if you give me an initial value problem where the initial value is specified on this interval, the interval from 0 to 1, then you'll be guaranteed a unique solution to the initial value problem that's valid on that entire interval, and the same thing for this interval. So let's look at the same example and try to solve things. Well, to solve this, we can use our general technique using an integrating factor. However, we don't even have to do that, because if we had put it in that same standard form, y prime plus 1 over t times y equals 1 over t times t minus 1 squared, and then use an integrating factor, the integrating factor would just tell us to multiply by t again and put it back in this form. In other words, this part here is already exact, and if we just integrate both sides, it tells us immediately that we get t times y. You can see the left side is just the derivative of ty with respect to t equals the integral of 1 over t minus 1 squared, which is easily seen to be minus 1 over t minus 1 plus some constant c. In other words, dividing by t, and you get y equals minus 1 over t times t minus 1 plus a constant over t. Now, let's say we have the initial value problem with this differential equation with, say, y of 1/2 equals 0. I've given you an initial condition that takes place at 1/2, and 1/2 is right here. Now, I put these two vertical green lines here. The green lines are at t equals 0. Remember, this is the t-axis. That's at t equals 0, and this one here is at t equals 1. So our general existence and uniqueness theorem tells you that given this initial condition with that differential equation, there should be a unique solution that's valid on the entire open interval from 0 to 1. In other words, between those two green lines. And we can easily figure out what it is. If we just plug in the initial value t equals 1/2 here to this equation, we get y of 1/2 is minus 1 over 1/2 times negative 1/2, which is exactly 4, plus c over 1/2, which is 2c, and this must be y of 1/2, which is 0. So when we solve for c, that tells us that c is negative 2. And if c is negative 2, we get y equals minus 1 over t times t minus 1 minus 2 over t. And if we plot what that looks like between 0 and 1, we obviously should check the solution, and I forgot to mention that earlier. Be sure you check that this is correct by differentiation and plug it in and check that the differential equation is satisfied, and check that the initial value is also obtained for this solution. So the solution goes through this point. When t is close to 0, we'll see that this minus 2 over t, you'll have here minus 2 over t, and when t is close to 0, this is close to 1 over t. So it still is negative and blows up. So the solution, it's going to be hard to draw this, is asymptotic here to the vertical line at, I didn't draw that well. The vertical line x equals 0. Oh, hard for me to draw this accurately on the tablet, but I'll try one more time. And then as t approaches 1 from the left side, we'll see that this blows up. T minus 1 would be negative, but with that negative sign, it becomes positive. This is just bounded. And so this part blows up, and we see the solution becomes big. Becomes big here. So there's a unique solution, has a graph something like that, on this interval from 0 to 1. If we take the same differential equation, which has this as the general solution, and we take the initial value problem of the same differential equation with a different initial value, and this time let's just take, for example, y of 2 equals 1. That means we'll need a solution that goes through this point, the point 2, 1. We can solve for c just by finding y of 2 using our general solution here. Y of 2 is going to be minus 1 over 2 times 2 minus 1. That's going to be negative a half plus c over 2, and we need this to equal 1, which is specified here. And it's easy to see that that implies c equals 3/2. So our solution, our unique solution is y equals minus 1 over t times t minus 1 plus 3/2, and we get the following solution. And now I want to be sure we erase our old solution here. We're only talking about a solution over here on the interval from 1 to infinity, and that solution will look something like this. It will blow up. I'll say this should be a 3/2 over t, so 3 over 2t. It will blow up as t approaches 1 from the right. And it will be very negative, is that right? If t is a little bit bigger than 1, this is negative, but very small. It'll go through this point, and it'll be maximum somewhere, I'm not sure where, and then the solution approaches 0 over to the right. So there'll be that unique solution that has a shape something like that. I'm sorry, let me fix this. I think here for y of t equal, c would have to be 3, not 3/2. Just change that. The general shape of the solution is still correct. I had just written that incorrectly. So here we can see our existence and uniqueness theorem guaranteed us the existence of a unique solution on the appropriate largest possible interval on which our coefficient functions were continuous, and we see that in these two examples. Let's look at another example, only this time this is a nonlinear differential equation. Here for this nonlinear differential equation, it's already in standard form. Y prime is f of t and y. That function of t and y, of course, doesn't really depend on t, but we can still think of it as a function of t and y. And in order to apply our existence and uniqueness theorem, we need to compute the partial derivative of f with respect to y, which is easily seen to be 2/3 y to the minus 1/3. You can see easily that f itself, y to the 2/3, is always continuous. df dy is always continuous, except when y equals 0. So if we ask where are both continuous, these are both continuous. At all points in the ty plane, except those with y equals 0. And let's find our solutions. How do we solve this differential equation? Well, it's a separable differential equation. If we write dy dt is y to the 2/3, you can write y to the 2/3 dy equals dt. When we integrate then both sides, we get 3 y to the, sorry, that would be y to the negative 2/3. Then when we integrate both sides, we get 3 y to the 1/3 equals t plus c, or y to the 1/3 equals t over 3 plus c over 3. Here c is an arbitrary constant, so I'm just going to write this as t over 3 plus c1, where c1 is arbitrary. It's just our other arbitrary constant divided by 3. Then we can write y is equal to t over 3 plus c1 quantity cubed. So that's our general solution to this nonlinear differential equation. I've shown here a direction field, and what I want to talk about is solutions with this initial condition, y of 0 equals 0. Well, here's the point 0, 0. And let me say I totally forgot one of the important things here. When the first step here, when we divided by y to the 2/3, we lost solutions when y equals 0. We should definitely note y equals 0. The 0 function itself is a solution. That's going to be very important for what I want to say. So we have the 0 function, which is a solution, and we have all of these as solutions. So here's the point 0, 0. You see one solution, which clearly follows the direction field, is this 0 function solution. Just stay horizontal at the 0 function. The other solution is of the form y of t equals here t over 3 plus c cubed. To have y of 0 equals 0, it's pretty easy to see that c must be 0. So we get y equals t over 3 cubed, which is easy to graph here. That looks something like this. It starts out very flat, and then it follows it starts out a little flatter than what I'm drawing, and then it follows down like that. And so here's the thing that makes this this differential equation very different from any linear differential equation. Through this one point, 0, 0, we have two different solutions. And in fact, there are a whole lot more that I haven't shown you. These are two different solutions either y equals t over 3 cubed, that's this solution, or y equals 0, that's this solution, and they both go through the same point so that there's not a unique solution to the initial value problem. Now, what might other solutions look like to the same initial value problem? Well, I claim you also have a solution that looks like this. If you have y equals 0 all the way up until 0, and then y equals t over 3 cubed after that, this hybrid solution is yet another solution to the differential equation that satisfies our initial condition. And the situation is actually even worse. There are many other solutions you could draw as well. You could have a solution that looks like one of these cubic things, meeting the x-axis here, or the t-axis there, then is flat for a while, and then continues. And that could actually be a solution, and again, it would go through the point 0, 0. So there are a whole lot of different solutions that all go through the point 0, 0. In other words, many, many, many solutions to this initial value problem that all look very different. But what does our existence and uniqueness theorem say? Our existence and uniqueness theorem says if I had picked an initial condition instead of y of 0 equals 0, I picked an initial point that's not at 0, 0, initial point that's not even on the y-axis, let's say I had an initial point here, then there's certainly some rectangle. In fact, I can make it a rectangle as big as I want as long as it doesn't touch the x-axis here, the t-axis I should say. As long as it stays away from the t-axis. On this rectangle, both f, that's y to the 2/3, and df dy, which again was a 2/3 y to the minus 1/3, are continuous. So on this rectangle, both f and df dy are continuous. That tells me there is a unique solution to the differential equation y prime equals 2/3 y that will exist at least on some small interval centered at the place where my initial condition takes place. But there's no guarantee as to how big an interval will work.